bottom minus derivative on the bottom times the top all over the bottom squared, right? That's your quotient rule. That's the way it's usually written in most books, that way. So the reason, and my Cal 1 students can attest to this, the reason I teach this way, which seems like a lot of you have been taught this way, which is good, is that the only difference between these two formulas is that that plus changes to a minus, and then you divide by g squared. That's the only difference between these two formulas. See that? But if you learn this one, then this and this look completely different, don't they? Like, these don't look like they're connected to each other in any way. So it's almost like you have to memorize two different formulas. So from here on out, I'm going to use these two versions, product rule and quotient rule.
So taking the derivative of either one, f or g, doesn't matter?
For product rule,
yeah.
It doesn't matter which one you do, which order you do it. You have to take derivative of one and then leave the other one alone and then switch it and then add them together. So you can do it in any order. But with quotient rule, the order is absolutely important. You have to do these two, subtract those two. And it's only because subtraction's not, right? 3 minus 4 is not the same as 4 minus 3, right? The order of subtraction matters. So you have to get this order right. Now, you could flip these two over, but yeah. All right, I'm going to proceed. Is there a question?
I was going to ask what the chain rule is, but I can look it up later.
Well, chain rule is, I mean, it's easy to write the rule out, but it's not easy to explain the rule. I'll put it up here. The chain rule says this. If you have y equals f composed with some other function g, so g is inside of f, then the derivative of that is the derivative of f first, evaluated at g, times then the derivative of the inside function g. That's the chain rule. But when you try and learn it this way, I think it's more confusing than to just get to a point where you see like outer, inner, and work your way in. But you're Cal 1 graduates, so some point you've shown some proficiency in chain rule, right? So let's see if we can't get that going again. This is a product rule. All right, so back to my product rule. What I'm going to do here to get this answer is I'm going to do derivative of the first one. What's the derivative of the first one? 2x times arc sine of x plus. So if you're kind of like keeping track of what we're doing here, this right here is like f prime times g. This right here is our f times our g, right? So we got f and g multiplied. We're doing f prime times g plus now g prime. What's derivative of? That was the thing we just did, right? So it's kind of ugly, but it's 1 over the square root of 1 minus x squared. That's a derivative of g right here. There was a plus here. And then times x squared, like that. That's the derivative. We could clean this up a little bit, right? Like maybe you slide that on top there. Maybe that's about all we do, but. All right, I want you to compare that to this. Take derivative of that. So now it's chain rule, right? That is not multiplication. You have inverse sine of, hear me say that? Inverse sine of x squared. When I say of, I'm talking composition. Here, did I ever say of? Well, I did x squared, right, times sine inverse x. There I'm saying sine inverse of x squared. So you have an inner function and an outer function. So when we take the derivative here, where do we start? When we take a derivative with composition, which function, the inner or the outer? Outer. So we're looking at that sine inverse function, we're taking its derivative, which is? 1 over the square root of 1 minus Yeah, the thing is what goes here. It's not x squared. It's whatever was in here squared. So it's the argument inside. So it's x squared squared, which I will turn into x to the fourth in a minute, times, now that this is where the chain rule comes in. You've taken care of the inverse sign. Now you take derivative of what's in here. 2x. So your answer here would be 2x on top of square root of 1 minus x to the fourth. Yeah? Let's do another one. Take the derivative of e to the tangent inverse of 4x. Well, by the way, this is a derivative. That looks like a 1. I mean prime, as in derivative. Yes?
Well, so like, isn't that the whole tangent inverse of 4x is in the x position, and the derivative of e to the x is the same thing?
Is itself, right? So we know from Cal 1 when we have derivative of, let's say, e to the u, right? The derivative of that is itself, right? Is itself times whatever the derivative of the u up here was, right? I mean, that's basically the derivative of e to something, right? So it should be e to the u, right? E to the u itself times what? This is the part you got to be careful with.
1 over 1 plus 4x squared.
Yeah, we're going to take derivative of this part now, right? Which is, we just did that. We just proved that formula, didn't we? I need to erase this. 1 over 1, what did you say? Plus whatever the whole thing in there is, 4x squared times 4, because we then have to take derivative of what's inside the tangent inverse. So we have an additional 4 out here. Is that too much going on there? I see some people running for the train. No? Look, this is a recap. I mean, the derivatives of tangent inverse and sine inverse, that's new. Chain rule, product rule is not new. So I understand it's day one. You might have to get yourself up to speed with product rule, chain rule, quotient rule. That might have to happen. Your homework will give you some opportunity to practice, all right? The problems have this. So please make sure you get help, all right? Who has a question about this? Like where any of this came from?
So the thing we're using is derivative of e to the u equals eu plus c.
Say again?
The rule we're using is derivative of e to the u, e to the power of u equals e to the power of u plus c. Is that it?
No, I'm using derivative of e to the u is e to the u times u prime.
U prime.
Yes.
Can you also do implicit differentiation with natural log?
You could, but it's probably not worth the effort. It's probably worse. Yeah, you could. Remember, the only time you really want to bring in a log on something like this is if you had x's in both positions. If you had x's in the base and the exponent, then you would need the log for that. Yes?
So just as a refresher, so when you're doing chain rule and you're doing, say, the derivative of the outside function, with respect to the inside, so
Mhm.
the difference between what we did now and before is that when we do the inverse trig functions, you're using the inside function in place of x, right?
Yeah, let me write it down like this. You know how we proved this to start everything off? We proved this was the first one we did, that this is 1 over square root of 1 minus x squared, right? That's what we did? Okay, if you wanted to make this more general, you could say this. If you're trying to take the derivative inverse sine of, let's say, u, of anything, it doesn't have to be x. It could be x squared, be some other thing, right? It will be 1 over the square root of 1 minus u squared, right? So I'm just replacing that with u. But then you have to multiply that times the derivative of this, right? So u prime. That makes sense? Is that what you're asking?
Yeah.
So if this right here was x squared, right? This would be 1 over the square root of 1 minus x squared squared times 2x. Let's try one more. How about this? Sine inverse of e to the x. What would the derivative of that be? 1 over 1 minus e to the x squared, right, like that, and then times, I'm going to write it this way, just so we can see the formula. Right? But the derivative of e to the x is itself. By the way, what's e to the x squared? What's another way I could write e to the x, that quantity squared? What's another way I could write that? E to the 2x. Because when you have something to a power, you multiply those two numbers, and 2 times x is 2x, not x squared, right? You're not doing x times x, you're doing 2 times x.
So and if you square root something to the power, then it's like the power divided by 2?
If you do square root,
E to the x, square root e to the x, is that e to the x power?
yes, if you did e to the x and you did square root, is that what you're saying?
Yeah.
That would be the same as e to the x, all of that to the half power, because that's what the square root really means.
Yeah.
But then that would be the same as multiplying those by that by a half, which you said divide by 2, right? Isn't that what you said?
Yeah.
Yeah, so that would be the same thing, e to the x over 2. That's the same. It's just, I'm just showing you there's other ways to look at things.
It's all coming back.
Yeah,
Like
get the
riding a
gears turning here.
Riding a bike.
All right, let's see here. What else do we have in here? We got a lot still. So here's where in the notes I talk about implicit differentiation. I talk about the reference triangle, right? And I prove what the derivatives of the inverse trig functions are. How much time? We have 20 minutes? Let's try that one. I'm going to write it down first, and then we'll do it. So if y equals the square root of the natural log of tangent inverse of x, right? So there's a weird function. Find y prime. All right, I'm going to give you a few minutes to see if you can work on it. Maybe you can talk to your neighbors. Make a friend. Make a friend. Make an enemy. I don't know. Lifelong friend. Stalker. Who knows? Right? I'll be right back. I'm just going to go get some water.
How does that do?
It's a triple composition, right? Three functions being composed together. Outer, middle, inner. If you have a question, if you're completely stuck, don't know what to do, just raise your hand. I'll come by and help out. Are y'all moving here? You getting anywhere, you think? Hey, did anybody win the lotto the other day? Somebody did, right? That won, right?
It wasn't in Texas.
You know how they won? They played, right? You got to play. You got to put something on the paper. You're never going to get it right if you don't play. It's okay to get it wrong.
Wait. It looks like
You just got to do something.
page 6
What?
of the fall. So what?
You're looking at the antiderivatives. You're not looking at derivatives. You're on the wrong page.
Well, I'm just
There you go.
too far ahead.
Yep, there we go. We're differentiating, right? So those are your differentiation rules.
Got you.
Start with that.
And then I don't see ln anywhere.
Keep looking.
Not needed.
Keep looking. Y'all help each other out. All right, were you going to ask a question?
Yeah, so I went into calculus since like last spring.
Okay.
So I'm more of like kind of trying to start this problem out.
So how many functions do you see there?
There's so you have 2 right here. And then I got the third one, which is the y prime.
You've got a square root, right? Square root. You've got a natural log, and then you've got tangent inverse. There are 3 different functions, right? One inside of the other, one inside of the other. Yes? So when you take a derivative of that, it's called composition. You start with the outer one. Okay, so what's the outer one?
Start with the square root.
Square root. Do you know what the derivative of the square root of something is? If I have square root of, let's say, u, and I want to take derivative, do you know what it is? It's okay if you don't. Okay, so go to your formula sheet. Hold on a second. Oh, these are your derivatives, see? Differentiation rules. Square root. Let's see if they have it on here. Don't see. They have the power rule. So it's actually the power rule, but I'll tell you this right now. You need to know this and have it memorized. This is 1 over 2 square root of u times u prime. This comes up a lot. So derivative square root of something is 1 over 2 times the square root of that times the derivative of what's in here.
Does it, so being that it is u, like, is u just the variable?
Use like an abstract idea. This could be anything.
Okay, yeah.
For us, it's a lot. It's natural log of tangent inverse of x, right? But generally, what you have here is square root of some junk, and then derivative of that is 1 over 2 times the square root of that junk times derivative of the junk. Okay, so this is what we have. This is our u, right? Go look at your problem.
So instead of that being, it would look like this. It would be
Let me look at yours. Okay, you did power rule. Yeah, that's right. Good. Did y'all look at each other? Yes. Are you kind of stuck also?
It just doesn't look right.
That's right. That's right. Yep. You have a question? Okay. Where you can check. Okay, I want to go through it. So by walking around, I can tell like people are all over the place, different levels. Okay. Are people very comfortable with chain rule? Got it. No problem. This is easy. All right. There are people who aren't sure even how to begin this. All right. So we got to get that ironed out. All right. If you're at a point where you're not sure, we got to get you up to speed. All right. Got to. That means you got to get help, tutoring, come to my office hours, something. Right. Let's see if we can't get you going. But you have to come for help. Right. You can't just show up next class and think that miraculously something happened between now and then. Right. You got to make some effort. Let me go through this. All right, let me go through this. There are 3 functions that are being composed here. You have an outer function, square root of x. A middle function, natural log. I'm sorry, square root. I said square root of x. Square root of something, right? Inside of that, natural log of something, right? Inside of the natural log, tangent inverse of x. So that's 3 functions being composed. When we take a derivative of composition, you always start with the outer function first. So I'm going to start with the square root. Derivative of the square root of something. There's different ways that people learn this, okay? Some people learn that when you take a square root, you rewrite it as x to the half, and then you do the power rule, which is fine. There's nothing wrong with that. Turns out to be 1/2, right? 1/2 comes out. X is negative 1/2. You subtract 1 from this power. That's your power rule. That's great. Nothing's wrong with that. You could use that. But I think it's better if you know that the square root of x, that when you take the derivative of it, you get 1/2 times the square root of x. That, to me, is cleaner formula. It's the same as this right here, right? It's the same thing, because if you drop this down to the bottom, you get 1/x to the half like that, right? Drop the negative exponent down, and then x to the half is a square root. So it's exactly the same as this. Yes? So in this class, when I take derivative of the square root of something, I'm always going to put this. That's what I'm going to do. If you do this, it's okay, right? That's fine. But I just want you to understand what I'm doing. Okay, so let me get to my derivative here. First thing is this square root. I'll highlight it in blue. That square root right there. I'm going to take derivative of that. Derivative of the square root of something is 1/, using this formula, 2 square roots, but I'm not going to put x in here, right? I'm going to put whatever was inside that blue square root. What was inside that blue square root? ln of inverse tangent of x, right? That's the first step. That's the first step. So now I've done the square root. Now I have to address the natural log. I have natural log of something, right? What's the derivative of natural log of something? 1 it, right? Whatever that is. So I'm just going to put here times 1 over what was in there. What was inside the natural log? It wasn't x, was it? What was it? Tangent inverse of x, right? So now I've taken derivative of the natural log of something. That's 1 over tangent of x, tangent inverse of x. And then finally, inside I have the tangent inverse x. What's the derivative of that? We just did that, right? We just proved that together. 1 over 1 plus x squared. That's your derivative.
I overthought that, so.
You overthought it?
Yeah, because I was trying to do all this extra stuff now.
Yeah.
I have a question.
Yes.
Like on a quiz or an exam, if there's any way, like I know we can simplify that by like factoring them.
That's okay.
If we did and it came out to be wrong, even though we had the right answer, is that
On a quiz, I want to make sure you can do this. Yeah. So look, remember I started out this class and I said, Cal 2 is hard, blah, blah, blah. Why is it hard? You've got to be proficient with product rule, chain rule, quotient rule. You've got to be proficient. You can't be eh. If you're eh with that, this is a real hard class. This is an example of a chain rule. This is a chain rule. You need to be proficient with this sort of thing. So please identify where your weaknesses are and let's address them. The sooner, the better, right? Okay. How are we doing? 9 minutes. I have just enough time. Maybe. I'm going to try this one. This is a problem that is very much like problems that you should have seen in Cal 1. But Cal 1 was a lot about like finding equations of tangent lines, right? Normal lines. So look at this one right here. Find the equation of the line that's tangent to this curve at the point 0, 0. So what we're trying to do here is this. I'm going to show you this visually. Go back to Desmos. I'm going to go to arc sine, arc sine, what was it, x squared y? xy squared. Plus That was it. So there's the graph of that curve right there, or graph of that equation. And I want to know the equation of the tangent line at that point 0, 0, right there. That's what I want to know. If you were to graph the tangent line, you know, what's the equation of that line? All right, so in order to do this, going back again to Cal 1, finding the equation of a tangent line means that we need to use this formula y minus y1 equals m times x minus x1. That's the generic formula for the equation of a line, right? This is the point slope formula. So we need a point on this line. Do we have a point on this line? Yes, 0, 0. So I can replace this with 0, this with 0, and I get y equals mx, right? That's it. That's just x. That's just y. So all I need to know now is what the slope is, right? What's the slope of this line? Well, the slope of the line is, because it's a tangent line, this is the derivative with respect to x at that point 0, 0. So that means I need a derivative. I need the derivative of this equation. I need dy dx of this right here. The issue with this problem is that that equation cannot be solved for y. You can't get y by itself on one side of the equation. So the only way to differentiate this is to use implicit differentiation. You have to take derivative on both sides with respect to x. So I'm going to now do implicit. So derivative with respect to x on the left, and then derivative with respect to x on the right. Let's do the right-hand side first, because it's easier. I only have 5 minutes, 6 minutes. When I'm taking derivative with respect to x of a sum, right, there's two terms, I can do them individually. So what's the derivative of x? 1 with respect to x, right? What's the derivative of y? dy dx, right? Because it's with respect to x. So I'm getting a 1 here plus the derivative of that with respect to x, which is dy dx. Why is it so important for me to realize that the derivative of y is not 1? Well, because I want to know dy dx, right? Like if you don't turn this into dy dx, you're never going to be able to solve for dy dx because you're never going to have it, right? So it needs to appear here somewhere. So that's derivative, that's 1, derivative here. Over here, I have chain rule, right? I have some chain rule I have to do here. I have inverse sine of something. I need to take derivative of that, and then the derivative of what's inside. So let's start with derivative of inverse sine. What's derivative of inverse sine? 1 over the square root of 1 minus, and then whatever this thing is, what do we call that thing inside of a function? What do we call it? The argument. The argument. So it's going to be 1 over the square root of 1 minus the argument xy squared, I'm not done, times now, chain rule, the derivative of what was in here, which is a product, which requires the product rule. So I'm going to do that right here. It's going to be, I'm going to do, using the formula that I said earlier with product rule, I'm going to do derivative of this first. What's derivative of x with respect to x? 1 times that plus, now this is the one that gets everybody, the derivative of y squared with respect to x. 2y times dy dx, I'm kind of out of room here, times, so you do derivative of y squared, the 2 comes down, 2y, but then you have chain rule, take derivative of y with respect to x. That's the derivative of y squared with respect to x. Times, now to finish the product rule is x. Because of time, I just need to finish this. Yeah, if you're not sure about this, just make a note. We can talk after class. All right, so that's my differentiation, my implicit differentiation. Now what I'm going to do, try and solve for dy dx at the point 0, 0. So I'm going to replace every x and every y with 0 in that equation and solve for dy dx. So let's see what happens when I replace. If I take this at the point 0, 0, let's see, I get 1 over, let's see, if I plug in 0 here, it's all gone, right? Let's just square root of 1 on the bottom, right? Okay, so it's going to turn out to be a 1, but I'm just going to put square root of 1 times, let's see, in parentheses, that becomes 0, and that's all 0. So isn't that whole thing 0? So 1 times 0, and then equals, over here, 1 plus dy dx. So left side 0, isn't it? So 0 equals 1 plus dy dx. So move the 1 over, negative 1 is the slope. Right, just move we get negative 1 equals dy dx. So now here's my final answer. This equation, I wanted to know what m was, right? What's the slope of that line? The slope of the line was the derivative at that point. The derivative at that point is negative 1, so replace that with negative 1, you get y equals negative x. And if we go back to the graph, I think you would agree that that's what the tangent line looked like there.
Yeah.
Go here. You probably could have told me that from the very beginning. There's the tangent line right there we just got. Now I gave you, that was a problem I gave intentionally so it's easy to look and visually check, right? Okay, so for your homework, let me look at this. I try and do this at the end of every class. I'll just double check that I don't want to add or subtract from the homework assignment. So you're supposed to do 3.5. It says page 181, but you're in an ebook, so there really aren't pages in the ebook. Let me see, 1.5. So let me just warn you a little bit. Numbers 1 and 5 are technically pre-cal problems. Those are problems that could have been asked in a pre-cal class. So they want to see how comfortable you are with the inverse trig functions and their domain restrictions. So just be warned, I didn't show any examples of those. Number 15 is proving the derivative of inverse cosecant. I proved inverse sine, I proved inverse tangent, right? There's 4 more. Your homework is to do one more of them. So that's where you can do reference triangle, all that stuff. And then 16 through 28 are all practice problems taking derivatives. Chain rule, product rule, quotient rule, it's all in there. Okay, there's a lot of practice there. And then 32 is a problem just like the one I did right now where you have